Okay, so let's start then. So, okay, fine. So, we're going to do a lot of the preliminaries about multivariable calculus and smooth manifolds today. So I'll try and go as fast as possible. So first of all, we define what is the derivative of a differentiable map from an open subset U of a normed vector space E, taking values in another normed vector space F. So we say that F is differentiable at a point X in U if there exists a bounded linear map df sub x from E to F such that f of x plus h minus fx, so this is the change in F, this is equal to dfx of h, so this is a linear function of the change in x, plus an error term which is little o of h, so that's small compared to the change in x. What little o of h means, this is a element of the vector space F. So to say this is little o of h means that the norm of this term, little o of h divided by norm h, this tends to 0 as h tends to 0. Okay. So the change in F is a linear function of the change in x plus an error term which is small compared to the change in x. Okay. This is the definition of the derivative. So let's just look at a simple example. If we take f from R2 to R, which is the norm squared function, f of xy is x squared plus y squared, then let's try to work out whether this function f is differentiable. So we look at f of xy plus a small change hk. So this becomes x plus h whole squared plus y plus k whole squared. So let's expand this. So we'll get x squared plus y squared, that is f of xy. And then there'll be terms which are linear in h and k. So there'll be a 2xh plus 2yk. So I can write that as the row vector 2x, 2y into the column vector hk, right? Plus I have quadratic terms h squared plus k squared. Okay. So this is equal to the norm of h comma k whole squared. So this is of course a little o of the norm of hk, right? Okay, because it's a square, so this divided by norm hk equals norm hk, which tends to 0 as norm hk tends to 0. And this part is a linear function of the vector hk. So that means we've got the required, this is you can think of this equation here as a first order Taylor expansion for f around x. So we've got this first order Taylor expansion for f, right? You have a constant term f of xy plus a linear term plus an error term which is small compared to the change in x, y. Okay. So that means that f is differentiable at x, at xy. So at a point P equal to xy in R2, and dfx, df at P, this is the linear map which I from R2 to R, which I write as a row vector 2x, 2y. This goes from R2 to R. Is this clear? Yes? Okay, fine. All right. So in general, so here we've found an explicit formula for the matrix of this linear transformation df, right? It is this 1 by 2 matrix 2x, 2y. So how do we find the matrix of DF in general? Well, we use what we did last time. We saw that this dfx for a differentiable map, for f differentiable from a vector space E to a non-vector space F, dfx acting on a vector H, this is equal to what we call the directional derivative nabla sub H of F at the point X. So this directional derivative is the limit t tends to 0, f of x plus th minus f of x over t. So this is an element of the vector space F, right? Okay, this limit exists, we showed, and this equals dfx at H. Okay. So this also gives you the uniqueness of the derivative, right? In the definition of derivative, this linear map which you get so that the error term is small compared to H, that linear map is unique because then that linear map acting on a vector, any such linear map acting on a vector H is given by this directional derivative of F in the direction of H, right? Which doesn't depend on the linear map. So that gives you the uniqueness of the derivative. Okay, so now if F goes from an open subset of Rn to, let's say, Rm, okay, and is differentiable, okay, then what is the derivative acting on the basis vectors Ei of Rn? So this will be the directional derivative of F in the direction of Ei. So this is equal to the limit t tending to 0, f of x plus tei minus fx over t. And this limit, we're just varying the ith coordinate by t, right? So we're differentiating with respect to the ith coordinate. So this is nothing but the ith partial derivative, del fi del xi, del f del xi at x, right? So this is an element of Rm. Okay. So if f is given by a column vector of functions, f1 up to fm, then it's easy to see that del f del xi, this is a vector in Rm. So at a point P, say, this is going to be equal to del f1 del xi at P. So this is a scalar up to del fm del xi at P. So what will the matrix of DF be? So the matrix of DFP will be the matrix whose columns are the images of the basis vectors E1 to En under the linear map DFP. So each column here will become del x1 at P up to del f del xn at P. Okay. And this, each column is, as we've seen above, the first column will be del f1 del x1 up to at p up to del fm del x1 at p up to del f1 del xn at p up to del fm del xn at p. Is this clear? Okay, so this is the matrix of the linear map df at p. It's just a matrix of partial derivatives of the components of f. Okay, so this is the matrix with ijth entry del fi del xj. Is this clear? Yes. Okay, so this is called any questions? Yeah. Okay, so I mean, you can see this example that we computed above is a special case where my f was from R2 to R. So the derivative will just be one row vector. And this entries are going to be del f del x and del f del y, right? So when I differentiate with respect to x, I'll get 2x. When I differentiate with respect to y, I'll get 2y. So the derivative is indeed this 2x, 2y. Okay. All right. But we gave an abstract definition of the derivative for maps between normed vector spaces without any coordinates, right? And that actually is often very useful. Let me give you an example. So remember, we defined the operator norm, right? If A is a linear map from E to F, then the operator norm is the sup over norm x equal to 1 of norm AX. So suppose A is a linear map from E to E, where E is a, let's say, a Banach space, okay? So then it's not hard to show that this L of EE, the space of bounded linear maps from E to E, is also a Banach space. Okay. And then if we take an element A of norm, operator norm less than 1, right, then notice that the norm of A squared, by properties of the operator norm, this is less than or equal to the norm of A times the norm of A, right? See, the operator norm satisfies the property norm of a composition AB is less than or equal to the product of the norms, norm A, norm B. Okay, that's easy to show. So this will be less than or equal to norm A squared. And similarly, in general, what you'll get is that norm of A power n, this will be less than or equal to norm A power n, okay? So that implies that the sum n goes from 0 to infinity of norm of A power n, this is less than or equal to the sum of norm A power n. And this is finite because norm A is less than 1. This is a geometric series. Okay. So that implies, because this is a Banach space, if I have a series of vectors which is absolutely convergent, then in a Banach space it is convergent, right? So that implies that summation without the norms a power n goes from 0 to infinity, this converges to an element of LEE. Okay. And if I call this sum, let's say S, so this sum converges. And you can see that I minus A into S is equal to S into I minus A is equal to identity, right? Okay, by the usual calculation for geometric series. So that means that S is equal to the inverse of I minus A. Okay. All right. Is this okay?
Yeah, it's okay.
Yeah. I mean, what happens is if you take I minus A into a partial sum of this series, right? So a partial sum will be I plus A power n. So when you multiply out, you'll get a telescoping series. So this will be I minus A power n plus 1, right? And this A power n plus 1, the norm of this is less than or equal to norm of A power n plus 1, which goes to 0. So this term, the norm goes to 0. So this converges to identity. And this converges to the sum S. So from that, by continuity of the composition of operators, this becomes I minus A into S is equal to identity. And similarly, S times I minus A is identity. Is this clear? Yeah. Okay. So now if I look at the map, let me call GLE to be the set of T from E to E such that T has a bounded inverse T inverse from E to E. Yeah. Then the first thing is this is open in L of EE because if I take any T which is in GLE, right, then I can write, if I take T plus another operator H, I can write this as T, because T is invertible, I can write this as T into identity plus T inverse H, right? And the norm of this term is less than or equal to norm of T inverse into norm of H. So this is strictly less than 1 if norm H is less than 1 over norm T inverse, right? So if the norm of H is less than 1 over norm T inverse, then the norm of this term is less than 1. So that means this sum by the above calculation, this belongs to GLE and this T belongs to GLE. So therefore the product belongs to GLE. So therefore T plus H belongs to GLE. Is this clear? Right? GLE is clearly a group, right? Okay. Is this clear? Yeah. So what does that mean? That means if I take the ball around T of radius 1 over norm T inverse, this open ball, this is contained inside GLE. Is this clear? Yeah. Okay, fine. Now I want to calculate I look at this map F from GLE. So this is an open subset of LEE. To LEE. T goes to T inverse. Okay. Right. So I want to see if this is differentiable. So I look at F of T plus H. So this is T plus H inverse. So I factor T plus H like I did here. So then this will become identity plus T inverse H inverse into T inverse, right? And now I can expand this using the geometric series for H small enough. This becomes identity minus T inverse H plus a sum n goes from 2 to infinity minus T inverse H power n, right? Okay. The whole thing into T inverse. So I'll get, this becomes identity minus T inverse H T inverse. So this is a linear function of H. Sorry, not identity. So I get T inverse. The first term is T inverse. So T inverse is F of T, right? So this becomes F of T minus T inverse H T inverse. So this is linear in H. Okay. And then I have an error term, which is given by multiplying this sum with T inverse. And what is the norm of the error term? Well, this is less than or equal to the sum of the norms. And the sum of the norms by the multiplicative property of the operator norm, this is less than the sum norm T inverse. I'll get a norm T inverse power n here. Yeah, so I'll get norm T inverse, norm H, the whole thing power n. Oh. And then I'll get norm T inverse here. Okay. And so when I sum this up, I will get norm T inverse, norm H, this thing whole squared divided by 1 minus norm T inverse norm H into norm T inverse, right? Okay. And so the whole thing is less than some constant times norm H whole squared, right? For norm H small. Okay, because I have this norm H squared and the rest converges to a constant as norm H tends to 0. Is this clear? Okay, so that implies that the error term E of H is little o of norm H. Okay, and this map, it's easy to see this is a bounded linear map in H, right? Okay, and so we get that F is differentiable and the derivative df at operator t goes from LEE to LEE. H goes to minus T inverse H T inverse. Is this clear? Yes? Okay. Are you there?
Yes, sir, it's fine.
Fine.
It's fine. So if you notice, this is actually a non-commutative version of the formula ddx of x inverse in one variable. This is minus x to the minus 2, right? In this case, what is the derivative? If I look at the derivative of this map, right, if I call this map f of x, then df at x will be the linear map from R to R. H goes to minus x to the minus 2 times h, right? So this formula that we've derived here, this is a higher dimensional non-commutative version of this formula, right? Is that clear?
Yeah.
Yes, sir.
Okay. And notice that even when E is equal to Rn, so that F goes from GLNR into MNR. So L of EE is just MNR. A goes to A inverse, right? The derivative df at element t, this goes from MNR to MNR. It sends a matrix H to the matrix minus T inverse H T inverse. So see, we've got a formula here without any coordinates, right? If we were to try and evaluate the matrix of this linear transformation from MNR to MNR, MNR has dimension n squared. That would be some matrix of order n squared by n squared, right? Which is impossible to compute. I mean, even if you compute the partial derivatives, it's meaningless, right? Just to see a matrix of n squared by n squared partial derivatives, it gives you no information, right? So trying to compute in coordinates in this case would be useless. You see, it's better to go coordinate free and work from first principles and derive the derivative from first principles. You get an expression which makes sense without any choice of coordinates here. Does this make sense? Yeah. Okay. So
Yes.
it's better to view the derivative as a linear map rather than as a matrix of partial derivatives. Okay, that's the point I'm trying to make here. Is that clear?
Yes, sir, it's fine.
Yeah, makes sense. Yeah. Okay. Okay. So I don't know why, for some reason, it's showing that this meeting has only 4 minutes left. It's supposed to be unlimited, but I don't understand why. For some reason, it's not showing that. I don't know why. So in case this meeting stops, maybe we'll start another one. Okay. Hopefully with the same ID, we should be able to start. All right. I don't know why this meeting is showing as limited. Normally it should be 2 hours. It's showing as only 40 minutes. So in case this meeting stops, maybe we can. Is it showing the remaining time is 3 minutes, 20 seconds for all of you as well?
Yes, sir.
Yes. Okay. So there's some problem with the Zoom account. So I guess we'll try starting another meeting with this same ID. If that doesn't work, then I'll send you an ID from my Zoom account. But let's try another meeting with this same ID, okay? Okay. All right. Okay. All right. So let me come back to the notes now. So, okay. So talking about derivatives, one special case of the derivative, which is important to note, is that if I take a curve, gamma, from an interval in R into a norm vector space E, which is differentiable as a map from R into E, then it turns out that what's called the tangent vector of gamma at time t, gamma prime t, this is defined to be a limit h tends to 0, gamma of t plus h minus gamma t divided by h. Okay, this limit is taken in the vector space E. This limit exists and equals the derivative d gamma at the point t applied to the vector 1. Okay, so d gamma at t, remember, is a linear map from R to E. So that acts on the vector 1 in R, right, to give you an element of E. Okay. And the linear map d gamma at t is determined by this gamma prime t, because by linearity, d gamma t of h, this becomes h times d gamma t of 1. So that becomes h times gamma prime t. Okay. So if you know gamma prime t, you also know d gamma at t. Okay. Fine. Okay. So now I want to state without proof what's called the chain rule. So if I have two maps, so first F going from an open subset of a norm vector space E to an open subset V of a norm vector space F, and then G going from the open set V and F to another norm vector space capital G. And if F and G are differentiable, then the composition G composed F from the norm vector space E to the norm vector space capital G is differentiable. And at any point P in U, the derivative of G composed F at P, this is the composition of the derivatives dg at f of p composed with df at p. Okay, we've got less than a minute. Let me stop this meeting and let's try starting another one. Okay. So I'm going to stop this now. Okay, so let's start then. Okay, so we have this chain rule which says that the derivative of the composition is the composition of the derivatives. Okay.
Are you sharing the screens? Yeah, now it's coming.
Now it's coming. Okay. Yeah. So if I have a composition of two differentiable maps, F and G, then the composition G composed F is differentiable. And the derivative of G composed F at P is the derivative of G at F of P composed with the derivative of F at P. Okay. So in particular, if we apply this to the case where the first map is a curve from R into the vector space E, and the second map is going from E to another vector space F, then if we look at F compose gamma, that's a curve in the vector space capital F, which is differentiable. And then the tangent vector of this curve, F compose gamma prime at T, as we observe, this is the derivative d of F compose gamma at T applied to 1. But that becomes, by the chain rule, df at gamma T applied to d gamma T of 1. And d gamma T of 1 is gamma prime T. Okay, so that tells us that F compose gamma prime at T is df at gamma T applied to gamma prime T. In other words, if I take a differentiable curve in E with tangent vector gamma prime T, then if I look at F of gamma, then the tangent vector to the image curve is the image of this tangent vector under the derivative. That's a linear map between these two vector spaces. So it maps this tangent vector to this tangent vector. Okay. Okay. So this will be useful for us frequently. Now, let me define what is a C1 map. So I've defined it for a map from Rn to Rm, but we can define this actually for maps between non-linear spaces. So if I have F from an open subset U in E to a norm vector space capital F, differentiable map, then this is C1 if the map, so you see at each point of U, we have the derivative at that point of U, a linear map. So this defines for us a map from U into the normed vector space LEF, which is the map P maps to DF at P. Right? So I'll say that F is C1 if this map is continuous. Okay? Is this clear? All right. So, for example, if F goes from, say, Rn to R, then DF at P, this is del F del X1, the row vector del X1 at P up to del F del Xn at P. So for F differentiable, okay, F is C1 if and only if this row vector is a continuous function of P. That's if and only if each component del F del Xi is a continuous function of P, right? So this is if and only if del F del Xi is continuous for all I, right? Okay, but in fact, it turns out, so given that F is differentiable, a necessary condition for it, a necessary and sufficient condition for it to be C1 is that del F del Xi's are all continuous. But in fact, it turns out that if you just know that the del F del Xi's exist and are continuous, then F is automatically differentiable. Okay, so that is a little non-trivial. I won't prove that. So in fact, it turns out that for a map F from an open subset of Rn to Rn, F is C1, so that means it's differentiable and the map P goes to DFP is continuous. This is if and only if del F del Xi exists and is continuous for all I. Okay, so note the important part here is the continuity of the partial derivatives. It's easy to give examples of functions for which the partial derivatives exist, all of the partial derivatives exist at all points, but the map is not differentiable. It may not even be continuous, in fact. Okay. So on the other hand, if you know that the partials exist and are continuous, then the map becomes differentiable and C1. Okay. All right. So I'm not going to prove this. This is a theorem. So, okay. So for C1 maps, we have some control of the function in terms of its derivative. We have what's called this mean value theorem. So again, I've stated it for maps from Rn to Rn, but actually it holds for maps between Banach spaces. So this is the mean value theorem. So here I should assume that E and F are Banach spaces. So EF Banach spaces. And F from an open subset of E to capital F C1 map. Oh, so let me assume that, okay, fine. So for all, maybe I'll just state it like this. So for all xy in U, such that the line segment joining x to y is also contained in U. Okay. We have that the norm of fx minus fy, this is less than or equal to the slope over z in the line segment joining x to y of norm of df at z, the operator norm, into the norm of x minus y. Okay. So the mean value theorem in higher dimensions, it is not an equality, it becomes an inequality. Yeah. So what does this mean geometrically? So this norm of df at z, remember the operator norm was giving you the maximum stretching of a linear map, right? So this norm of df at z, this gives you the maximum stretching of the derivative at each point z along this line segment. That means the maximum infinitesimal stretching of f, right? Okay. And so what it's saying is that if I divide by this norm x minus y, then the mean value theorem takes the form that this ratio f norm fx minus fy divided by norm x minus y, this is the macroscopic stretching of the map f. This is less than or equal to the maximum infinitesimal stretching of the map f. Okay. And so how do you see this? Well, you take the line segment x to y and you break it up into small pieces. You take a partition of this line segment into very small pieces, right? And you look at the images of these partition points, right? So that will give you some polygonal path if I join them by straight lines, okay? And these differences over here, if I look at this f of ti plus 1 minus f of ti, right? Or maybe I call it zi plus 1, if these points are zi. This difference is approximately equal to the derivative df at zi acting on zi plus 1 minus zi, right? Plus something which is little o of norm zi plus 1 minus zi. Okay. And so when I add these up, what I'll get is that the norm of fx minus fy, this is equal to the norm of the sum. So the total change in f from x to y is the sum of the small changes in f from zi to zi plus 1. Okay. And this is less than or equal to the sum of the norms of these, and that is less than or equal to the sum over I norm df at zi into norm zi plus 1 minus zi plus something which is small compared to the sum of the norms of zi plus 1 minus zi. Okay. And the sum of these norms, this is equal to just norm x minus y. So this is little o of a constant. So this goes to 0. And this sum is bounded by the SOAP of norm dfz. Z belongs to xy into the sum of norms here, norm zi plus 1 minus zi, plus a term which is little o of 1. And this sum is equal to norm x minus y. Okay, so now you let the mesh of the partition tend to 0, and then you'll get the mean value theorem. Is this clear?
Yeah, it is clear. But the thing that you have written at the last, that is the sum of the norm of zi plus 1 minus zi. That's true in the real line. Right? Oh, you are on real line. Okay.
I'm on the line segment, right? These are my
Yeah,
lines.
yeah. Okay.
Sum of these norms is equal to the full length, right?
Right. In art, this
On a-
is true, but in higher dimensions.
No, nothing finite dimensional. I'm in a line segment in a norm vector space.
Yeah.
The point is I'm on a line segment, right? So on a line segment, the sum of norms equals the
Right.
the total
Yeah,
difference, right?
Yeah.
I'm on a line segment, so
Okay.
yeah. Is this okay? So basically what it's saying is that at each point, if you can stretch by at most this SOAP of norm dfz, then on the whole, you can stretch by at most this SOAP. Okay. Is it clear? That should be intuitively clear, right? If at each point you can stretch by a factor of at most 2, then the whole stretching from x to y can be at most 2. Is that clear?
Yeah, this fine.
That makes sense? Okay. So that's the mean value theorem. And then using the mean value theorem, it's easy to show that if, let's say, the derivative is 0 at all points, then f is constant, right? Because then, at least in a neighborhood of each point, in a ball around each point, if you apply the mean value theorem, this SOAP of norm df is 0. So that means fx is equal to fy for all y in a ball around x. So that means f is locally constant. So if your domain is connected, then f will become constant, right? Is that clear? Yes, okay. Okay, fine. So let's carry on then. So then I want to state something which we'll use in its full generality, the inverse function theorem for Banach spaces. Towards the end of this course, we will actually need it in infinite dimensions for Banach spaces. So if f is a C1 map from an open subset of a Banach space E to a Banach space F. And if there is a point x0 in the domain D, such that DF at the point x0, yes,
I have a question. Excuse me. Sorry for that.
yes, go ahead. Yeah.
So this MVT is true for any convex subset of the Banach space.
Yes, correct. Any open convex set, yes.
Open convex subset, because
Right.
we are taking the segment, and because it is compact, so supremum is exists.
Correct.
So
That's
why, yeah.
That's right. Yes,
Okay.
yes.
Fine. Thank
Since
you.
it is compact and F is C1, the supremum is
Yeah.
finite. Correct. That's right. Yeah. I
Fine.
forgot to
Thank
mention that. Thank you. Yes.
Okay.
yeah. That's right. That's right. Okay. So, okay. So the inverse function theorem says, if at a point the derivative at x0 is an invertible linear map from E to F, that means it's a bounded linear map with a bounded linear inverse. Okay. Then there exists open neighborhoods U of x0 and V of F of x0, such that F from U to V is a C1 diffeomorphism. So here C1 diffeomorphism means a C1 map with a C1 inverse. Okay. That is a C1 diffeomorphism between open subsets of Banach spaces. Okay. All right. Fine. And similarly, let me state for you the implicit function theorem. So the implicit function theorem is for maps defined from a product of Banach spaces to E cross F to another Banach space G. So if I have such a map which is differentiable, I can define its first and second partial derivatives with respect to the variables in E and F. So the first partial derivative d1f at x0, y0 is the following. I fix y equal to y0, and then I look at this as a map from the Banach space E to the Banach space G. X goes to f of x comma y0. And I take the derivative of this map at x0. Okay. So if f is differentiable, this map will also be differentiable. And you look at its derivative at x0, that is the first partial derivative. Similarly, you can define the second partial derivative. That will be a linear map from F to G, which you get by fixing x0 and taking the derivative of the map, y goes to f of x0 comma y. Okay. And these partial derivatives are given in terms of the full derivative. So d1f is a function of a vector h in E that is equal to df of h comma 0. Okay. And similarly, d2f of a vector k in F is equal to df of 0 comma k. Okay. Now the implicit function theorem says, if I have three Banach spaces E, F, G, and F is a C1 map from an open subset of E cross F to G, and if I have a point x0, y0 in my domain D, such that the second partial derivative, d2f, at a point x0, y0, so that's a linear map from capital F to G. If this second partial derivative is invertible, then if I look at the set where f of xy is equal to f of x0, y0, yeah, then locally this looks like the graph of a C1 function from E to F. So the precise statement is there exists neighborhoods U of x0, V of y0, and there is a unique C1 map G from U in E to V in F such that G of x0 is y0 and the set of xy in the domain where fxy equal to fx0, y0. If I look at the intersection of this with U cross V, so this is a product neighborhood of x0, y0. This is equal to exactly the graph of G restricted to U. So it's the set of pairs x comma gx where x is in U. So let me just draw you a picture. So here you have E and here you have F. So I'm taking an x0 and I'm taking a y0. Okay. And what it's saying is there are neighborhoods U here of x0 and V here of y0, So that if I look at this product neighborhood, so that's like a rectangle here. Then in this rectangle, there is a map G from U into V, so that this set, this is a level set of the map little f. So this is f of xy equal to f of x naught y naught intersect u cross v. This is equal to the graph of a map G. Okay, so a point here is of the form, there's an x here, and this will be of the form x comma gx. Okay, so x is the implicit function defined by this equation, right? Where y is defined implicitly as a function g of x. Okay. Is this clear? Yeah. Okay. Is this clear? Yeah. This is the implicit function theorem. Okay.
Yeah.
Okay, so we've stated the inverse function theorem and the implicit function theorem. Now I want to get to higher derivatives. Okay, so what are higher derivatives of a map between Banach spaces? Okay, what are higher derivatives? So suppose first we have a multilinear map T from E cross E cross E, say K times to F. Okay. Then you can define the norm of this multilinear map similar to the way you define the operator norm of a linear map. The norm of a multilinear map is the sup over norm V1 equal to 1 up to norm Vk equal to 1, the norm of T of V1 to Vk. Okay. And we say that the multilinear map is bounded if this norm is finite. Okay. So again, you can show similar to for linear maps, a multilinear map is continuous if and only if its norm is finite. Okay. And we have this similar inequality for the norm of a multilinear map. The norm of T of V1 to Vk for any vectors V1 to Vk is less than or equal to norm T into norm V1 up to norm Vk. Okay. Yeah. Okay. So then we define this space of bounded multilinear maps, MKEF. This is the space of multilinear maps T from E cross E cross E to F, whose norm is finite. Okay, so if E and F are Banach spaces, this will also be a Banach space. Okay. So now we can come to what is the second derivative of a map between Banach spaces. So a map F is a differentiable map F from E to F. We'll say this is twice differentiable if the map, so remember we had a map DF, which was going from U in E to LEF, right? So this map, we want this map to be differentiable. So this is now a differentiable map from E into LEF, okay? So if this is differentiable, then the second derivative is defined to be the derivative of this map. So the derivative of this map, DF, that will be a linear map from E to the space of linear maps from E to F, right? So the second derivative, D squared F at P, is an element of this following space, L of E of L of EF. Is this clear? Okay. Yeah. And this space now, linear maps from E, which take values in linear map into the space of linear maps from E to F, this can be identified with the space of bilinear maps from E cross E to F. How is that? So given an element T here, so that's a linear map from E into LEF, right? This will give you a bilinear map T hat. So T hat has to act on two vectors in E, and give you a vector in F. So T hat applied to two vectors V1, V2 is the following. You first apply T to the vector V1. So that gives you an element of LEF. Now that can act on another vector. You let that act on the vector V2. Is that clear? So this will become a bilinear function of V1, V2, right? Okay. And it's not hard to show this map is an isomorphism between these two norm vector spaces, which moreover preserves the norm. Okay. So the norm of operator norm of T here is equal to this norm of T hat here. Okay. All right.
Yeah.
Is this okay? All right. Okay. So now how do we calculate this second derivative acting on a pair of vectors VW? So we're going to do that now. So the second derivative we can think of as a bilinear map from E cross E to F. Okay, so this is what I was trying to say earlier. The second derivative is no longer a linear map. It is a bilinear map from E cross E to F. Okay. So the second derivative becomes a bilinear map. So how do we calculate this bilinear map? So first, let's make the following observation. So the second derivative means we're going to be differentiating the first derivative, right? So differentiating means we can differentiate it along curves or along straight lines, right? So that will give me a family, a one parameter family of linear maps. So suppose I have a curve of linear maps, T goes to AT, okay, in LEF. So this is a curve in the vector space LEF. So if this is differentiable, then if I apply each of these linear maps AT to a fixed vector V, that gives me a curve in the vector space F. The derivative of this curve, ddt of ATV, it's easy to show this is equal to the derivative of this family of linear maps, ddt of AT, that's again a linear map applied to the vector V. Okay. So you can show this as an easy exercise. This is not difficult. So now suppose that F is a twice differentiable map from E to
Just
F.
interacting. Hello,
Yes.
sir. So what is the map AT? Can you please recall?
No, I'm just saying, suppose you're given a differentiable curve in LEF. T goes to AT. Then
All right.
ddt of ATV is equal to ddt of AT applied to V. So this is true for any curve AT in the space LEF. Okay.
Sure.
That's all I'm saying. This is just a simple fact you can prove. Okay. So we're going to use this to calculate the second derivative. So how do we do that? So let's see. So let's look at the following. So I take two vectors V and W in my vector space E. Okay. And I take a point P in the domain U. Now I look at the derivative df at the point P plus TV, and I apply this to the vector W. Okay. So this family here, df of P plus TV, this is my family AT that I was, this will be the family AT that I was saying here. So by this property here that I have above, if I take ddt at t equal to 0 of this will be ddt at t equal to 0 of this family of linear maps applied to W. Now the derivative of this family of linear maps, by the chain rule, this is going to be the derivative of the map, x goes to df at x, applied to the derivative of the curve P plus TV. Now the derivative of the curve P plus TV is just the vector V, constant. So, and the derivative of the map x goes to df at x, that is the second derivative, right? So this derivative, ddt at t equal to 0 of df of P plus TV, this will be nothing but d squared f at P applied to V, right? Okay. And then that I apply to W. Now this, by definition, this is the bilinear map d squared f at P applied to V comma W. Okay. Okay. And what happens if I differentiate f twice along this straight line p plus tv? So if I take the second derivative at t equal to 0 of f of p plus tv, then this is ddt at t equal to 0 of the first derivative of this. Now the first derivative of this by the chain rule, this is df at the point p plus tv applied to the vector v, right? V is the velocity vector of this straight line, p plus tv. So this ddt at t equal to 0 of df of p plus tv applied to v, this by the previous line, this is the same as d squared f at p applied to v comma v. Okay. So that means this second derivative along the diagonal v comma v, this is given by differentiating twice f along the straight line p plus tv. Is this clear?
Yeah.
Okay. So how do we relate this to second order partial derivatives? So suppose f now, let's come to a more concrete setting. So suppose f is going from Rn to R. Okay. Suppose f is going from Rn to R now. So we can talk about its second order partial derivatives. So what will the second order partial derivative del squared f del xi del xj at p be? So this by definition is del xi of del f del xj. That is by definition ddt at t equal to 0 of del f del xj at the point p plus t ei, right? Now this term inside del f del xj of p plus t ei, that is by definition, that is equal to df at the point p plus t ei applied to the vector ej, right? Remember the partial derivatives were nothing but the derivative applied to the basis vectors ej, right? So this becomes ddt at t equal to 0 of df of p plus t ei applied to ej. But this by the computation we did above, this is nothing but d squared f applied to ei comma ej. D squared f at the point p, there's a p missing here. This applied to ei comma ej. Is that clear? Yes? We did this calculation just above here, right? ddt at t equal to 0 of df of p plus tv applied to w. This is d squared f at p applied to v comma w. So here I'm just substituting this. V is equal to ei and w is equal to ej. Is that clear? So then I get this, right?
Right. Yeah. Right.
I'm just putting v equal to ei and w equal to ej. That's it. Okay. So what does that tell me? That tells me that the value of this bilinear map on the basis vectors ei, ej is nothing but the second partial derivative del squared f del xi del xj. Okay. Okay. Yeah. So this collection of second partial derivatives, these turn out to be nothing but actually, if you remember your representation of multilinear functions, taking values in R, right? They were determined by their values on k tuples of basis vectors, right? So a bilinear function will be determined by its values on pairs of basis vectors ei, ej, right? These are in fact the coefficients of d squared f with respect to the basis ei star tensor ej star, right? If you remember. Yes, your linear algebra that we did earlier last time.
Yeah.
Right. So these are the coefficients of, so these second partial derivatives are the coefficients of this bilinear map d squared f at p with respect to the basis ei star tensor ej star, okay, of the space of bilinear functions. Okay, so we have less than a minute, so I'll start this same meeting ID again. Okay, I'll stop this meeting and start another meeting with the same ID. Okay, So see you then. Okay, so let's continue then. Okay. So what about higher derivatives? So just like the second derivative turns out to be a bilinear map, okay, higher derivatives will turn out to be multilinear maps. They can be identified with multilinear maps. So let's see how. So this will be by induction. So you define a sequence of vector spaces. L1 of EF is just L of EF. And then you define LK of EF inductively as L of E comma LK minus 1 of EF for K greater than or equal to 2. Okay. Then it's not hard to show that LKEF, this will be naturally isometric and isomorphic to the space of bounded K multilinear maps, MKEF. Okay. And we can define a map F from E to F to be K times differentiable inductively if F is K minus 1 times differentiable and the K minus 1th derivative. So this is a map from U in E to LK minus 1 EF. Okay. P goes to DK minus 1 F at P. If this map is differentiable, then we say that F is K times differentiable. Okay. So then what will the Kth derivative be? DKF at P. This will be the derivative of this map, DK minus 1F at the point P. So DK minus 1F is going from where? E to LK minus 1 EF. So the derivative of this map will be a linear map from E to LK minus 1 EF. In other words, DKF at P will be in the space L of E comma LK minus 1 EF. That is by definition LKEF, and that is identified with MKEF. Okay. So in this way, the Kth derivative is identified with a K multilinear map from E to F. Is that clear? We've done it for K equal to 2. For higher K, it's similar. All right. That's all I'm saying. Okay. So the higher derivatives are multilinear maps. All right. Higher derivatives are multilinear maps. And it turns out that if I take a map from Rn to R, then the kth partial derivatives, del kf, del xi1 up to del xi, k at a point P, this is nothing but the kth derivative, dkf at the point P, applied to the basis vectors ei1 to eik. Okay, just like we saw for the second derivative, the same holds true for higher derivatives. Okay. Is this clear? Yeah. The statement, I'm not proving this. I'm just asking if the statement is clear. All right.
Yeah, it's clear.
Yeah. Okay. And so a map F from an open subset of Rn to Rm, this is defined to be Ck if F is K times differentiable and the kth derivative dkf, now you think of this as a map which at each point P gives you a K multilinear map dkf at P. This map from Rn, this should be Rn to the space of K multilinear maps from Rn to Rm, this map should be continuous. Okay. So it turns out that this F is Ck if and only if, this is a theorem, all partials of order less than or equal to K exist and are continuous. Okay. So in other words, we are saying more here. If all partials of order less than or equal to K exist and are continuous, then the derivatives of F of order up to K which are multilinear maps, all of those multilinear maps will exist. Okay. Those higher derivatives will all exist as multilinear maps. Okay. And f is C infinity or smooth. It's defined to be C infinity if f is Ck for all k. That is if and only if all partials of all orders exist and are continuous. Okay. All right. And if U, V are open subsets in Rn, then a map f from U to V is a C infinity diffeomorphism if f is C infinity and has a C infinity inverse G from V to U. Okay. All right. And now, just like we saw for the second derivative, that if I differentiated f along the straight line p plus tv twice at t equal to 0, then I got the second derivative applied to v comma v. Similarly, if I differentiate k times, if I take dk dtk at t equal to 0 of f of p plus tv, this will give me the kth derivative dkf at p applied to v comma v comma v k times. Okay. Remember, this kth derivative I'm thinking of as a multilinear map. So it is going to act on k vectors. All right. Is this okay? Yeah. Okay. So now let me state for you Taylor's theorem. So suppose f from an open subset of Rn to Rm is a CK map, and you have a ball of radius r around a point x, which is contained in U. Then in this ball, if I take x, if I take h of norm less than r, then if I take a point x plus h in this ball, then f of x plus h I can write as fx plus a linear term in h, dfx applied to h, plus a quadratic term in h. So this will be 1 over 2 factorial, the second derivative d squared f at x applied to h comma h, plus a cubic term 1 over 3 factorial d cubed f at x. So this is a trilinear map applied to h comma h comma h, and so on up to 1 over k factorial dkf at x applied to h comma h comma h k times, plus a remainder term rk of x comma h, where this remainder term, there's an explicit formula for this, from this formula, using the fact that dkf is a continuous function of x, one can easily show that this formula implies that this remainder term is little o of norm h to the power k. Okay. All right. So this remainder term is small compared to norm h to the k. Okay. This kth term, this is actually going to be a polynomial of order k in the coefficients of h. That will be of order norm h to the k. So this remainder term is small compared to the last term. Okay. So this multivariable Taylor formula, how do you see these terms as polynomials? Well, let me just show you. So if you take, let's say, the first term in the Taylor formula, right? So you take dfx of h. This is dfx of summation hi ei. So this is summation dfx ei into hi by linearity, and dfx ei is nothing but the partial derivative, right? Del f del xi. So you get the first order Taylor polynomial. This is a linear polynomial, right? This is summation over I del f del xi into hi. Okay. Now, if similarly, if you take the second term, d squared f, so 1 over 2 factorial d squared fx at h, So this will be 1 over 2 factorial d squared f x applied to summation hi ei sum over I and sum over j hj ej. Okay. So by bilinearity, this will be 1 over 2 factorial sum over ij d squared f at x applied to ei comma ej into hi hj, right? And d squared f at x applied to ei ej, this, as we've already seen, this is the second partial derivative del squared f del xi del xj, okay, into hi hj. Is this clear? So this is a quadratic polynomial in H. All right. Is it clear? Yes.
Yeah, it's clear.
Right. So similarly, the kth term 1 over k factorial dkf at x applied to h. Sorry, this should be h comma h. Sorry. There's not an h here. This is h comma h. Right. Similarly, this will be applied to h comma h k times. This will be 1 over k factorial sum over k multi-indices I1 to ik between 1 and n, and then you'll have del kf del xi1 del xik, okay, into hi1 product up to hik. Is this clear? All right. Yes.
Yeah, it is fine.
Okay, so same calculation as for the first and second derivative. Okay, so this is how the Taylor theorem, the way I've stated it, it actually gives you an expansion of a polynomial of degree k plus an error term, which is of little o of norm h to the k. All right, that's the Taylor theorem. Okay, so right, so here I have a little write-up about multilinear functions. So this we already did. We saw that if ei is the basis of v and ei star is the dual basis, then the tensor products ei1 star tensor eik star, these k-fold tensor products are a basis of v star tensor k, which is identified with the space of k multilinear functions from v cross v cross v k times to r. And any k multilinear function alpha, its expansion with respect to this basis is given by sum over I1 to Ik, alpha of ei1 to eik, ei1 star tensor eik star, right? So in particular, if we apply this to the kth derivative, so dkf at p of a map from Rn to R, so this is an element of Rn star tensor power k. It's a k multilinear function from Rn cross Rn k times to R. So the expansion of this will be dkf at p will be sum over I1 to Ik, dkf at p applied to ei1 to eik into ei1 star tensor eik star. And this term dkf at p applied to ei1 to eik, this is nothing but the kth partial derivative, right? Del kf del xi1 del xik. Okay. So these mixed partial derivatives, these are nothing but the coefficients of this multilinear map with respect to the basis ei1 star tensor eik star. Is it clear now? Okay. So all these partial derivatives of order k, if you just look at it as a collection of numbers, it doesn't seem to have any structure, right? But actually it does. These all fit together to give you the components of a multilinear function, a K multilinear function, with respect to a basis for the space of multilinear functions. Okay. Is it clear?
Yeah, it's clear. Yeah.
Okay. So that is what the kth partial derivatives are. They are the coefficients of the multilinear function with respect to this basis, the natural basis, EI1 star tensor, EIK star. Okay. That is what the kth partial derivatives are. And we know that we have equality of mixed partial derivatives, right? If f is ck, where k is at least 2, right? So if if I take any partial derivative of order L less than or equal to k, and I take any permutation of order L, then the partial derivative del LF del xi1 up to del xil is the same as the permuted partial derivative, right? Del LF del xi sigma 1 up to del xi sigma L, right? Okay. So what does that mean? That means that if I look at the kth derivative, then so if I look at any derivative of order L less than or equal to k, so then DLF of EI1 up to EIL, this is equal to this kth partial derivative del LF del xi1 del xil. This is equal to the permuted partial derivative del LF del xi sigma 1 del xi sigma L. This is equal to the kth derivative applied to the permuted basis vectors EI sigma 1 up to EI sigma L, right? Okay. Is that clear? So that means that the kth derivative or the Lth derivative, sorry, this should be an L here, not a K. This should be an L. The Lth derivative, this is invariant under permutations of the basis vectors, right? So that will, by multilinearity, that will tell you that the Lth derivative is invariant under permutations of any vectors, right? Okay. Is that clear? So applied to vectors V1 to VL is the same as applied to vectors V sigma 1 to V sigma L. Okay. Is this clear? Yeah. If this holds for all basis permutations of basis vectors, then it will hold for permutations of all vectors, right? By multilinearity. Is that okay?
Yeah, it's fine.
Right. So what does that mean? That means this K multilinear function or L multilinear function, this Lth derivative, is a symmetric multilinear map, right? It's invariant under permutation. Is that clear?
Yes, right.
Right? It's a symmetric multilinear map. Yeah. So it's not just any multilinear map, it's a symmetric multilinear map. Yeah. So in particular, what happens for the second derivative? The second derivative then becomes a symmetric bilinear form, right? but a symmetric bilinear form on Rn, that can be identified with a symmetric matrix, right? Yes, right? Symmetric bilinear forms, are identified with symmetric matrices, right? So in this case, what happens? This second derivative, d squared f acting on vectors vw, this is the bilinear form sum over ij, del squared f, del xi, del xj at p up into vi wj. This I can write as a matrix H times V inner product with W, right? Where H is the matrix of this symmetric bilinear form. It's the matrix with entries del squared f, del xi, del xj, right? So this is a symmetric matrix, right? Yeah. This is a symmetric matrix which is called the Hessian matrix of F, okay? So this matrix comes about from the correspondence between symmetric bilinear forms and symmetric matrices. Is that clear?
Yeah.
Right? Any symmetric bilinear form in is of the form VW goes to V transpose AW, right? For some symmetric matrix A, right?
Yeah, and the Hessian is basically the matrix of that bilinear.
Exactly. The Hessian is just the matrix of that bilinear form. It's the matrix of that symmetric bilinear form. Okay. Okay, so that's what the
And
second
the
derivative.
higher order derivatives are exactly that. I mean, the hypermatrix of the kth multilinear form. Something like the higher order derivatives.
The higher derivatives, the higher order the derivatives are just k multilinear functions. They're symmetric k multilinear functions. That's all we can say, right? I mean,
yeah, but there are some matrices as well, like del kf divided by del xi power alpha I dot del xl power alpha at mod of alpha is L, right? Something like that.
I suppose you could define some sort of matrices, I suppose, yeah. But I mean, the correspondence between symmetric matrices and bilinear forms, it's only for bilinear forms, really. For multilinear, higher linear, trilinear, quadrilinear, you don't have real correspondence with just, single matrices, right? So
Right.
you don't have that correspondence.
I mean that's why I mentioned the term hypermatrix.
Yeah, I don't know what hypermatrices are, honestly. I don't know what those are. I don't know what those are. Yeah. But essentially, it's the same thing. It's nothing but packaging the coefficients of a tensor, right? It's just packaging the coefficients of a tensor.
Right.
It's nothing but that. It's nothing but that. Yeah. So,
like in trilinear form, the matrix is like a three-dimensional matrix. So
right. It's basically nothing but the coefficients of the tensor, right? Of your multilinear function.
Exactly. Right.
It's nothing but the coefficients of your multilinear function. So that, if you want to call it a hypermatrix, you can. But I mean, it's just a trilinear function. So it's just its coefficients with respect to the basis, right? It's just its coefficients. Okay. Now, we can note the following, what is called the second derivative test in higher dimensions. So first note that if f is a differentiable function and p is a local maxima or minima of f, then if I restrict f to any straight line passing through p, let's say p plus tv, then f of p plus tv as a function of one variable t, this will also have a local maxima or minima at t equal to 0. So that means its derivative at t equal to 0 will be 0. So we get that 0 is equal to ddt at t equal to 0 of f of p plus tv. But this is equal to dfp of v, right? So that means that dfpv is 0 for all vectors v. Therefore, at a local maxima or minima, the derivative df at p is 0. Okay? Just like in one dimension, the derivative vanishes at a local maxima or minima. So in higher dimensions, the linear map df at p, it vanishes at a local maxima or minima. Okay? So now, suppose you have a C2 function f, okay, from Rn to R. Then if P is a local maxima of f, then the Hessian matrix is less than or equal to 0. So look, remember, it's a symmetric matrix. So we can talk about it being greater than or less than or equal to 0. That means that inner product of HV comma V is less than or equal to 0 for all V, right? It's negative semi-definite, okay? And there is a partial converse to this, that if the first derivative vanishes, DFP is 0, and the Hessian is strictly negative definite, okay? So Hessian is strictly less than 0. That means that inner product HVV is strictly negative for all non-zero vectors V. So it's negative definite. Then P is a local maxima of F, a strict local maxima, okay? So the proof is quite simple. If I take any vector V in Rn, then the function f of p plus tv, this has a local maxima at t equal to 0. So that means by the usual calculus for one variable, the second derivative is less than or equal to 0, right? Of f of p plus tv. And this second derivative, we've already seen, this is equal to d squared f at t applied to v comma v. And that is equal to inner product hv comma v. So therefore, hv comma v is less than or equal to 0. Is this okay? All right.
Yes, sir. Yeah.
And conversely, suppose that the Hessian is strictly negative, okay? Then look at the maximum of this quadratic form, hv comma v, on the unit sphere, right? So on the unit sphere, this quadratic form is strictly negative. Therefore, its maxima will be also strictly negative, right? The maxima is attained on a compact set. So this will be strictly negative. So let's call this epsilon naught, this maxima of the quadratic form on the unit sphere. Now we use the second order Taylor theorem. For h small, f of p plus h will be fp plus the first order term dfp is 0, we're assuming. So there's no first order term. Then the second order term is the second derivative. So 1 over 2 factorial into the second derivative, which is the same as the quadratic form associated to the Hessian matrix, plus the remainder term, which is little o of norm h squared, right? Now, by bilinearity, this h, Hessian into h comma h, I can write this vector h as h divided by norm h, and h divided by norm h and into norm h squared, right? So then h over norm h is a unit vector, and this quadratic form applied to a unit vector is less than or equal to epsilon naught. So therefore, this will be less than half epsilon naught h squared, norm h squared, right? And the remainder term is small compared to norm h squared. Therefore, the sum of these two, because epsilon naught is negative, the sum of these two will be negative for h small enough, right? This norm h squared term will dominate this little o of norm h squared term, right? So this sum will become negative. So therefore, this will be strictly less than f of p for h small and non-zero. Is this okay?
Yes, sir.
Yeah, so that means that f has a strict local maxima, okay? If the first derivative vanishes and the Hessian is negative definite, okay? All right. So that's the second derivative test in higher dimensions. Okay. Now there's one calculation I want to do, which is again a derivative. It's a derivative of the determinant function. Okay. So we can think of the determinant function as a map from MNR, the vector space MNR of n by n matrices, to R, right? It's a function on MNR. Okay, it's a polynomial function, so it's continuous, and well, it's polynomial, so you know it's going to be differentiable because all its partial derivatives of all orders exist and are continuous, right? They're just polynomials, in fact. Okay, but let's work out what its derivative is, right? So we can think of this as a multilinear function from Rn cross Rn cross Rn to R, right? It's a multilinear function of the columns of the matrix, okay? So think of it as a function of n columns, n column vectors, okay? All right. So now if I take a matrix H, which has column vectors little h1 up to little hn, notice that the norm of each hi, this is the norm of h into ei, right? That is less than or equal to the operator norm of h, because ei is a unit vector. Okay. So each norm of each column is less than or equal to the operator norm. Okay. So therefore, if I take a determinant of a matrix where k of the columns come from the vectors hi's, so k of the vectors, the columns are of the form hi1 up to hik, and the others are the standard basis vectors, then the absolute value of this will be less than or equal to the norm of the determinant as a multilinear function into the norms of these vectors. So the norms of the ei's are 1, and the norms of the hi's are less than or equal to norm h. So I'll get a product of norm h k times, right? So this will be less than the norm of the determinant into norm h power k. In other words, if H is a small matrix, then this determinant of a matrix with k columns coming from H, that will be little big O of norm H power k. Okay. So in other words, if there are at least 2 columns coming from H, then this will be big O of norm H squared. Okay. This will be of order norm H squared at most. All right.
I mean, this is just less or equals to norm h per k because the operator norm of det is 1, right?
The operator norm of det is 1. That possibly is true. I'm not sure. I haven't thought about that actually. Yeah. I don't know. The operator norm of det, you'll have to work it out, right? It's
I'm just
yeah. No, see, the operator norm, I mean the norm of a multilinear function, right? That will be the sup over norm v1 equal to 1 up to
1,
norm
right,
v1
right. Norm
equal
vn equals to
1.
1, right?
Of mod of det of v1 to vn, right? So I don't know how to estimate that. Yeah, I don't know what the norm will be. I'm not sure it's 1. I don't think so. Yeah, I don't think it's 1. Yeah. I don't think it's 1. Yeah, it may or may not be. I'm not sure. I don't know. Yeah, I don't know. Yeah, I can't say. Yeah, what we know is that it's finite, right? Because it's a polynomial function. So, I mean, the supremum over
how will
the
you
unit
evaluate the
vectors.
norm of the multilinear function? So all
This,
of your
look,
columns
I
are
defined
vectors
this.
having norm 1.
Look, I defined this way back, right? I defined this over here. Where is it?
Yeah, so like in the determinant, all of your columns are vectors having norm 1.
Yes.
Right?
So does that mean that the determinant is of modulus less than or equal to 1? I don't know. Yeah, actually, no, you're right. It's true, because if the norm of the matrix is less than or equal to 1, if the norm of the columns, no, that's no, I'm not sure. I'll have to think about it. Yeah, I'm not sure.
Okay, sure.
Yeah, I'm not sure. Yeah, I'm not sure. No. It's not necessarily no. See, you know that the norm of, if I look at the matrix with columns v1 to vn, where vi's are unit vectors, right? That means that matrix, if I call that matrix, say, H, then H of EI, that has norm equal to 1, right? So I know that for the basis vectors, H maps them to vectors of norm equal to 1. But that does not mean that any unit vector goes to a vector of norm less than 1, right? Some unit vector could go to some big vector of norm bigger than 1. That's possible. Right? That's possible. Yeah, that's possible. Just if you just know that the basis vectors map to unit vectors, that's not enough, right? if they are not orthogonal, if they are not an orthonormal basis, then you don't know anything about the other vectors, other unit vectors. So no, that won't be true in general. That won't be true in general. Yeah, I'll let you think about it. Okay, let me carry on. Okay. Yeah, so let me just compute the derivative of the determinant. Okay. So let me look at the derivative of the determinant at the identity. Okay. So the determinant of identity plus h, this is determinant of E1 plus H1 up to En plus Hn. So by multilinearity, I can expand this. So the first term will be where all the columns are coming from the identity matrix, determinant of E1 to En. Then the second term will be, the next terms will be where there is exactly one column coming from H, right? So that will be a sum over J, determinant of E1 to, this should be a J, Ej minus 1, Hj, Ej plus 1, En, right? Okay. And then the other terms will have at least two columns coming from H. So those will be of norm less than a constant times norm H squared, right? Of modulus less than a constant times norm H squared. So when I add those up, I'll get something which is big O of norm H squared. All right. Okay. So now what do I get? I get the first term is determinant of the identity plus I get a sum over J, and then Hj I can expand as sum over I, Hij, Ei, right? Okay, I expand Hj. So then this becomes a sum over J, sum over I, Hij, determinant of, so okay, there's this I and J have got mixed up here. This is a typo. This should be E1 to Ej minus 1, and this should be an Ei, okay? And then Ej plus 1 up to En. So in this determinant, you'll see that this determinant is 0 unless I is equal to J, right? If I is not equal to J, then the same column will be repeated twice and this determinant will become 0. So the only terms which remain is when I is equal to J, then you just get Hii into 1, okay? So you'll get the sum Hjj here. In other words, you'll get the trace of H, okay? So you get determinant I plus trace H plus little big O of norm H squared. So that's a little O of norm H. So that means the derivative of the determinant at the identity is nothing but the trace, okay? This linear map. Okay. So this will be useful for us later when we talk about change in volumes and infinitesimal change in volumes. You'll get the trace and so on. Okay. So let me stop here. Unless there are more questions, there's less than a minute. So let me stop. We'll continue next time. Okay. Okay.
An interesting question to think about the operator norm of determinant.
Yeah, I don't think that's true about the operator norm of determinant. Yeah. I don't think it'll be 1.
Yeah, I understand why that's not one.
Okay, there's less than a minute, so this is going to stop anyway. So let me stop. Okay. Okay then.